Hi! The topic of this video is special right triangles in their angles and their measures. So we're going to look at what exactly makes these triangles here so special. I'm going to guess it's their angles and their measures. We're going to explore two big questions. First, what do we know about the special right triangles? And then we're going to look at how we can use the Pythagorean theorem to find out what else makes these triangles special. So basically we're going to look at the angles and how we can come up with the triangles, and then we're going to look at them using the Pythagorean theorem and find out what the ratios of the sides are. The first triangle we're going to look at is the 30, 60, 90. And to examine this triangle, we have to prove that it exists by building it. Not with a hammer and nails, just in our minds. To build our 30, 60, 90 triangle, we have to first create an equilateral triangle. An equilateral triangle is over here, and you can see that it's got all of its angles congruent to each other and all of its sides congruent to each other. If you don't know the notation, this little dash here means that those sides are congruent to each other. So we start with this thing. And how do we get 30, 60, 90 from it? Well, we're going to drop an altitude. What does it mean to drop an altitude? It just means basically that it's the height of that thing, and the height is perpendicular to the base. As you can see here, we've got a line drawn from the top vertex to the base of the triangle. That gives us a 60-degree angle and a 90-degree angle. The question becomes then, what is that missing angle? 180 minus 90 minus 60 equals 30. 30 plus 60 plus 90 is 180. So that angle is 30. Whew. We've got a 30, 60, 90 triangle by dropping this altitude here. All right, so now we've got these two triangles that we have created here, are 30, 60, 90, and then this one right here has to also be a 30, 60, 90 because of this postulate right here, angle side angle. And that means that these two 30, 60, 90 triangles have what we call corresponding congruent sides. This side here is congruent to this side here, and we've got those sides between these corresponding congruent angles here and here. Therefore, angle, side, angle, angle, side, angle, making the triangle on the right and the triangle on the left congruent to each other. And when they're congruent to each other, it means that they have corresponding congruent parts. That gives us triangle congruence, but more importantly, the fact that this segment here is congruent to that segment there. If these two segments here are congruent, then that means that this is the midpoint of this segment, which means if this whole segment is equal to this whole segment and this is the midpoint, this has to be half of this. Voila, we've constructed a 30, 60, 90 triangle. And now that we have this 30, 60, 90 triangle constructed, we can talk about its side lengths. So when we looked at the equilateral triangle before, remember we said that this altitude here cut the bottom side in half. And that means that whenever we drop this altitude here, that this distance here has to be half of the hypotenuse of the 30, 60, 90 triangle. The question is, though, how do we figure out what this altitude's height is? Well, that is really easy when we use our old friend, the Pythagorean theorem. So if we substitute in here that A is half of C, then we have two variables in terms of C, and we can solve all the way down here for B in terms of C. So then we have that the side B, the altitude of that triangle, is going to be radical 3 over 2 times the hypotenuse. This will come in later when we're looking at trigonometric ratios. We'll use this fact to determine some of those. The next special right triangle is the isosceles right triangle, otherwise known as the 45-45-90 triangle. We're going to have a similar look at this as we did to the 30-60-90. As you may or may not know, an isosceles triangle is one where we have a pair of congruent angles if and only if its sides opposite of them are congruent. In other words, if we have a triangle where this angle and this angle are congruent, then the sides opposite them must also be congruent. Or conversely, if we have a triangle where this side and this side are congruent, then the angles opposite of those sides have to be also congruent. This is an if and only if statement because we can start by assuming the angles as our conditions and concluding that the side lengths are congruent to each other, or vice versa, start with the side lengths being congruent to each other and show that the angles are congruent to each other. This here is a specific example. I've got 45-45-90 because that's the triangle we're going to talk about. So let's look at how we figure out those side lengths. Here we're going to go in one direction of that isosceles triangle theorem that I presented before, and we're going to prove if two pairs of adjacent corresponding angles are congruent, then the pairs of corresponding sides that are opposite of them have to also be congruent. We're going to do that by, again, dropping an altitude and showing that we've got congruent triangles on the inside. And if those triangles are congruent on the inside, then the sides have to be also congruent because they're corresponding in those triangles on the inside. So we drop our altitude over here, and we've again got a 45-45-90 triangle, which means this is also 45-45-90. And then we have this special theorem over here called angle side congruence. This isn't the only way that we could prove that the two smaller triangles in here are congruent, but it is a way. So basically, if I've got two angles that are next to each other and then a side after them that's congruent, then those triangles have to also be congruent, and that is definitely true here. So we've got two smaller triangles that are congruent, this one over here and this one over here, and we've proven that if we've got that angle congruent to that angle, then the sides opposite them have to also be congruent. And this gives us, in our specific example here, an isosceles right triangle. Now let's set up the ratios. All right, here we're going to use a similar way of finding the ratios, i.e. our friend the Pythagorean theorem. In this case, we're looking here. That side is congruent to that side, so we're going to let our b equal to a. And when we plug it into our Pythagorean theorem here, we get a squared plus a squared equals c squared, and we can solve for c in terms of a, which gives us that the hypotenuse is the square root of 2 times a. Nice. When we get to trigonometric ratios and we're figuring out what the ratios are for specific angles, we kind of have to modify that because we'll be fixing the hypotenuse as 1 and figuring out what the leg lengths are. But for now, this is a fine ratio to consider. So imagine we're on a coordinate plane here. We let our legs equal to 1. We can construct a length of the square root of 2, and then we can use a compass or a circle tool or something to take that distance and project it onto the number line, and we can figure out exactly where the square root of 2 is. And that makes this particular triangle here pretty powerful because we can use it to construct a distance that is irrational. All right, so what can we conclude from all of these things that we looked at here? Well, we know that 30, 60, 90 triangles are constructed from an equilateral triangle, which is just a special case of an isosceles triangle. Remember, all equilateral triangles are isosceles because our conditions for isosceles are that we have to have two congruent angles or two congruent sides to show that the opposite angles or sides are congruent. So in an equilateral triangle, we have that condition. We've got three congruent sides, and that's 3 meets the condition of at least 2. Since the 30, 60, 90 triangles formed by the equilateral are congruent, we can show easily that the shortest side, the one that's across from 30 degrees, is half of the hypotenuse because we just cut it in half by dropping that altitude, remember. We can also use the Pythagorean theorem to deduce that the remaining side is half the square root of 3 times the largest side. And as I said before, this will come back into play when we're looking at trigonometric ratios in regards to the unit circle that we construct. We construct a right triangle with a hypotenuse of 1 on a circle, and this will give us the sine and cosine of some of these angles. In an isosceles right triangle, 45, 45, 90, the hypotenuse is the square root of 2 times the length of the leg. So remember, we said we can use this to construct lengths of the square root of 2 and multiples of the square root of 2. So square root of 2, 2 times the square root of 2, just depending on how we construct originally those lengths. So if I've got a 1 by 1 equilateral triangle, that's going to be square root of 2. And then depending on how I change those lengths, I'm going to get a different length there on my hypotenuse. And that is what you need to know about special right triangles. Thank you for watching.